And that was pretty clear from Siri or whoever she was. Let me switch over to share screen as I usually do and get that set up, and we'll get started here. Let's see, share. All right, with any luck, this will work. All right, let's see what we got here. Okay. All right, let me enlarge this. Try to lock it into a frame. I have taught this course in the past at 8 a.m. in the morning, and that required me to get up at like 3 o'clock in the morning in order to, prepare beforehand, and it wasn't too satisfactory for me. But now, even if I wanted to, I couldn't do that because I've got a daughter I have to get off to school and things like that. So my schedule is fairly constrained by things that I have to do. In addition to that, the department needs a certain number of classes outside of what they call prime time. And prime time is 9 a.m. to 3 p.m. I think that's what it is. Because everybody wants to have their office hours, during, excuse me, not office hours, class time, in that time. So 8 a.m. is actually an easy slot if you want to get it. But also after 3 is easy slots. All right, anyway, we're helping out the department by giving them, the required percentage outside of prime time. All right, I'm going to get started here with this, just a slight review of what we did last time. There isn't much to review, really. But the topic we're moving into here is the quantum mechanics of charged particles in electromagnetic fields, possibly time-dependent fields. So just to review a little E&M, the electric and magnetic fields are given in terms of potentials by the formulas I've written down here. I've been calling the scalar potential capital phi because I want to distinguish it from the azimuthal angle phi, and sometimes it gets in the way. But that's all it is a scalar potential. The vector potential is A. These formulas are in Gaussian units, which explains the 1/c if you're not familiar to seeing that there. I have an appendix on converting SI into Gaussian units if you want to take a look at it. It's not as bad as you might think. And the Gaussian units are definitely better for this course. In any case, Maxwell's equations for E and B guarantee the existence of a scalar phi and a vector A such that these equations hold. However, although these potentials exist, they're not unique. And they can be changed from one form to another. This is called a gauge transformation. A gauge transformation is specified by a function of in general, both space and time, what I call the gauge scalar. A goes into A plus the gradient of F, and phi goes into phi minus 1/c df dt. That's a gauge transformation, giving us primed potentials. And if you use the prime potentials to calculate E and B, what you find is that E prime is equal to E, and that in the B prime is equal to B. That is to say that the potentials are invariant under a gauge, excuse me, the electric and magnetic fields are invariant under a gauge transformation. So I prefer to think about this in the following way. I like to think of this way is that the potentials phi and A, here they are, phi and A, contain a physical part because by forming derivatives of them, you can calculate E and B, which are physical. On the other hand, they also contain a non-physical part. That's the part which is changed by a gauge transformation, and it can only be established by convention. So in any case, this is a basic feature of using potentials in electromagnetic theory. Now, when I say that E and B are physical, what I mean is that you can measure them physically. I mean, the reason you can measure them is because of the force law. Force is mass times acceleration. This is a classical formula. Force times acceleration force is mass times acceleration, which is the charge Q times the electric field, plus the velocity V over C crossed into the magnetic field. And so by measuring the forces on charged particles, you can determine, a given point of space or a given time, you can determine what E and B are. They're freaking measure E and B. On the other hand, there is no way to measure the vector or the scalar potential. There's no such thing as an A meter or a phi meter. And I think I explained a little bit about that last time. That's because it contains this non-physical element. Not unless you wanted to commit yourself to a gauge convention. That would be something you could do. Then you could say what the value of A and phi are, with respect to that convention. All right. Now, if you're just doing classical E&M, looking for particle orbits, most people would work with these equations here, which are expressed in terms of E and B. And so the lack of uniqueness of the potentials doesn't matter because the potentials aren't used here at all. On the other hand, if you want to write down the classical Lagrangian and classical Hamiltonians, they do require the potential, curiously enough. So the classical Lagrangian, for example, is this. It's mv squared over 2, which is, of course, the kinetic energy, minus the potential energy, which is the charge q times capital phi, which is allowed to be a function of position and time. And if there's a magnetic field, there's another term around, which is q over c times the velocity v dotted into the vector potential A, which is also allowed to be a function of x and time. So the Lagrangian has to be expressed in terms of the potentials. From this Lagrangian, you can compute the canonical momentum, which is dl dv. This is just all standard classical mechanics I'm quoting here. dl dv is mv coming from the first term, the kinetic energy. The potential energy doesn't contribute, but the v dot a term does and gives you a plus q over c times the vector potential A. And I've talked about this before in connection with making the distinction between the kinetic and canonical momentum. The mv part is what we call the kinetic momentum, and it's just the usual definition of the momentum in elementary courses. But the momentum that occurs here is the canonical momentum, which is the dl dv, and it's got this extra term in, at least in the case in which there's a magnetic field around. If there's no magnetic field, then there's no difference between the canonical and the kinetic, and you don't have to worry about it. We will, however, spend a fair amount of attention in this course on problems with magnetic fields, so it's going to be important to know the distinction between these two. All right, anyway, going through the standard procedures of classical mechanics, you end up with a Hamiltonian, which is a function of position, momentum, and it actually also depends on time in general. And for this problem, it turns into the following. It turns into 1 over 2m, the momentum p minus q over ca, which is a function of x and t in general, quantity squared, plus a q times phi of x and t, like so. And this is the Hamiltonian, then, classical Hamiltonian, for the motion of a charged particle in an electromagnetic field.
I don't understand.
Yeah.
They're right there.
Yeah.
I have to call because now I have to, schedule it. Yeah.
Excuse me, are you making a question? Are you asking a question? Or was did sound get turned off? Okay, anyway, let me continue. So this is a remarkably complicated expression for such a simple problem, and one has to ask why. Part of the reason is that the P minus Q over CA, if I look at this kinetic, canonical equals kinetic plus the Q over CA, the canonical momentum minus the Q over CA is the kinetic momentum, which is the same thing as MV. So this square bracket thing squared is mv squared, so it's m squared v squared, and then divide by 2m, then the entire first term just turns into 1/2 mv squared. So what you see is that in this Hamiltonian for a charged particle in a general electromagnetic field, the first rather complicated looking term is actually nothing but the kinetic energy. It's just expressed in a complicated way because of the necessity of using the canonical momentum here. And here's the potential energy. So it's just kinetic plus potential. It's just what you'd expect for a Hamiltonian, and that's what it is. Anyway, this is a situation regarding the classical Hamiltonian in E&M. All right. Now then, we are interested in the quantum Hamiltonian, or the quantum description of charged particles in electromagnetic fields. And in the absence of further information, one of the questions we're going to have is, what is the Hamiltonian? And without any further information, one of the ways of at least guessing the Hamiltonian is to borrow the classical Hamiltonian and reinterpret it as a quantum operator. Actually, in order to do that, what we do is we regard H not as an ordinary function, a C number function of C numbers X and P, but rather as a function of operators X and P, which are now required to satisfy the canonical or Born-Heisenberg commutation relations. And if we do this, then then we obtain a quantum Hamiltonian. And this is a procedure that's sometimes called canonical quantization because it involves taking the canonical coordinates of a classical system and just simply, if you will, you just wave your hands. and reinterpret them as quantum operators. And so, excuse me, let me get myself comfortable here. So canonical quantization is one of the methods of obtaining at least a guess for a quantum Hamiltonian. Now, the question is that guess correct? And the answer is that, well, there's no way to tell without comparing it with experiment. You can use classical mechanics as a guide to guess what the quantum Hamiltonian is, but you're not proving anything by doing that. And so let's do that. Now, if we do that, then you have to ask the question, well, how good is it? How good is this as a quantum Hamiltonian? And the answer is that it depends on the question you're asking and how refined a description you want. But in many cases, it works pretty well. It does leave out some important physics, however, such as spin, assuming the particle has spin. It leaves out the relativistic effects, no wonder, because the classical Hamiltonian was non-relativistic. And it leaves out effects of emission and absorption of radiation and magnetic interactions between multiple charged particles. And there's quite a few things that are not contained in this Hamiltonian. So we'll see some of those refinements as we go on with the course, but at least for this point, at this point in the argument, this is a place to start for that Hamiltonian. Okay, one of the issues that arises in quantum mechanics, of course, is that momentum and position don't commute with each other. And if you multiply this expression out, this complicated expression for the kinetic energy, you're going to get things that involve P and A. I think one way to handle this is to define an operator called pi. And pi is basically just the kinetic momentum. That's just another notation for it. So it's equal to mv classically. That's all it is. But it's also the same thing as the canonical momentum P minus Q over Ca. It's this complicated expression that appears everywhere, like this. And so the kinetic energy is pi squared over 2m. If you want to write it this way, it's pi squared. I'll write it as pi vector squared over 2m. That's what it's equal to. So one of the ways of interpreting this Hamiltonian so that you don't have ordering issues is to commit yourself to a definite ordering. Write it this way: as 1/2 1 over 2m of pi dotted into pi plus a q phi. And if you write it that way, where pi is understood as this entire expression, you've got a definite product of a dot product of two Hermitian operator vectors, and the result therefore is Hermitian. They're identical, so they commute with each other. So the product of two Hermitian, remember the theorem, the little theorem, very simple theorem. Product of two Hermitian operators is Hermitian if and only if they commute. Well, if the two operators are identical, they do commute, so the result is Hermitian. So this is a Hermitian product. And we will use this then as an interpretation, as the interpretation for the quantum Hamiltonian. This is an example, by the way, of where ordering issues arise in passing from the classical Hamiltonian to the quantum Hamiltonian. All right, so that's the basic setup then of the quantum Hamiltonian for charged particles and electromagnetic fields. There's a couple of issues that arise here. One of them is what about probability density and current? Let me say some things about that. I previously explained the probability density and current for a simple kinetic plus potential, as to say, without a magnetic field, but now let's generalize it to include a magnetic field. Generalization is pretty easy if you think about it the right way. Let's do it this way. It turns out that what you want for the probability density rho, which in general is a function of both x and t, is the obvious definition is just the square of the wave function. In other words, the same as it always was with no change. And as far as the current is concerned, there's a way of writing the current so that it has the same form, both with and without magnetic fields. And it looks like this. I think this is what I quoted earlier. It's the real part of psi star of x and t, then the velocity operator in the middle, multiplied by psi of x and t on the right-hand side, like so. Now, as far as the velocity operator is concerned, if you were just dealing with the kinetic plus potential problem, as I say, without any magnetic field, this would be the momentum divided by the mass, which of course is the same thing as minus IH bar gradient divided by the mass. And if you plug that in here, then you get the correct expression for the current in a simple kinetic plus potential problem. However, in the presence of a magnetic field, this needs to be replaced by 1 over m times pi, which is 1 over m P minus Q over Ca, which is the same thing as a differential operator is 1 over m times minus IH bar gradient minus Q over CA. And so you use the definition, whatever definition of velocity applies for your system is different depending on the Hamiltonian. You use that there. And if you do, you get the right answer for the current. This formula for the current, let me box it so we just draw attention to it. The formula for the current looks like an expectation value. Obviously, it's got psi star psi, but we don't do an integral, so it's actually not an expectation value. It's really the integrand of an expectation value. And you have to be careful because the velocity operator can only act to the right. We don't allow it to act to the left because it's not a matrix element. I mean, to make it act to the left, you'd have to do integration by parts to eliminate, boundary terms to get the right answer, to get the answer you usually expect, which is to say that it doesn't matter which way you let it act. But there are no, but here you see there's no integration, so you can't do that. Anyway, so the V acts to the right. It has to be understood in the use of this formula. But anyway, so this is a useful formula for that. So there's the current and probability density for charged particles in magnetic fields. And by the way, these do, as expected, satisfy the continuity equation, del dot rho divergence J is equal to 0. And I'll leave that as an exercise for you to check by substituting these definitions into the Schrodinger equation and working out the time derivatives to see that it's correct. The continuity equation, Griffiths in his book, I'm grateful to him for his certain insights. He makes the interesting point at a certain place in his book. He may be talking about charge, but it applies equally here to probability. You could have conservation of charge without having a continuity equation. For example, you could have charge disappear here and then instantaneously pop up over in San Francisco, and that would conserve charge, but it wouldn't satisfy the continuity equation. The continuity equation says the conservation of charge takes place in effect by the motion of charge from, continuously from one place to another. That's the idea. There's a current vector that represents the flux of charge. Well, now here we're talking about a flux of and a density of probability, which, as I keep saying, don't represent individual systems, but rather an ensemble. But still, as a description of the ensemble, they move continuously, you see, in the same way that what Griffiths is saying about charge. All right, in any case, they do satisfy these equations. And these continuity equations are usually regarded as an essential part of the physical interpretation of the Schrodinger equation. All right, now here's another issue that arises with the particles in magnetic fields. As in classical mechanics, the Hamiltonian is expressed in terms of potentials, not in terms of electric and magnetic fields. I didn't, here it is up above, written out explicitly. I think I intended this to be the classical Hamiltonian, but with a reinterpretation of symbols, this becomes the quantum Hamiltonian. The first complicated term is still the kinetic energy, 1/2 mv squared. If we define the velocity operator by means of, where is it down here? It's, let's see, did I find it? Yeah, did I find it? Yeah, here's the velocity operator defined this way. It's just the kinetic momentum divided by the mass. Yeah, pi over m. But with the velocity operator so defined, even in quantum mechanics, this Hamiltonian is still kinetic plus potential, and here's the kinetic energy, and there's the potential there. Now, in any case, it is again a curious fact that the Hamiltonian formulation, which is all you have in quantum mechanics, you don't have Newton's laws, require the use of potentials. You can't write it in terms of E and B. Actually, people have written papers where they try to do it in terms of E and B, and it can sort of be done, but it's not local and it's not very attractive. So doing it in terms of potentials is essentially for most practical purposes, is a necessity. All right.
Yes, sir.
Yes.
I'm wondering. Here we just wrote down that the V operator is P over M, and then that's just P is the operator given by the del. So then does that mean that
that's right. That's right here. That applies when you have a kinetic plus potential Hamiltonian with no magnetic field. If you have a magnetic field, then you have to follow the lower line here.
Okay, so that means P is the The canonical momentum.
Yeah. So if there's no magnetic field, of course, there's no difference between them. But if there's a magnetic, and you can see that if I just said A equals to 0, I get the earlier result. So this second result for including a magnetic field is more general, but it includes the earlier case as a special case. If A is equal to 0, there's no distinction between the kinetic and canonical momentum. They're both the same. If there is a magnetic field, then you have to worry about the difference, because you have to say, which of these two corresponds to the operator minus IH bar gradient. The answer is it's canonical momentum, not the kinetic. All right. In any case,
is there a reason why P happens to be the canonical momentum?
Which P which you mean?
P, like the momentum operator.
Well, I mean, there's two momenta, and they both have operators. Which momentum operator do you mean? I think what you're asking is, why is the canonical momentum minus IH bar gradient?
Yes, that's what I'm asking.
The answer is that it's a generator of translations, just as it is in classical mechanics. That's one of the ways of understanding it, at least. It's the canonical momentum. So canonical momentum is what Hamiltonians have to be expressed in terms of. If you don't do that, you don't get Hamilton's equations in classical mechanics. That's why you need the canonical momentum even in classical mechanics if you want Hamilton's equations to be valid.
Mm-hmm.
All right, but keep thinking about that, because this is one of the curiosities and interesting features of problems of particles in magnetic fields. It's one of the things we'll pay some attention to. That's actually quite an interesting issue. In any case, let me proceed to the next topic, which is related to this, which is that if the Hamiltonian is expressed in terms of A and phi, we just decided earlier that A and phi are not unique, but can be subjected to a gauge transformation. Well, it sure looks like if I replace A by, A prime minus grad F, and similarly with phi prime, I'm going to get a different Hamiltonian. Does that mean that the Hamiltonian depends on the gauge? Is that how it works? Is it only valid in one gauge? That sort of doesn't make sense, does it? You ought to have a Hamiltonian description. This formula, in some sense, ought to be valid regardless of the gauge. And this is in fact true, but it takes a little bit of understanding. It takes some work to understand that. So let me work on that problem. Actually, before I deal with that problem, I want to make a digression into a subject which is useful in its own right, but will also help us with this gauge. So the next project is to do the gauge transformation on the Schrödinger equation for a particle in an electric and magnetic field. But as a digression, before I do that, I want to talk about something else, which is unitary transformations on the Schrödinger equation, because it turns out the gauge transformation can be interpreted as a unitary transformation, and so it's a special case of that. Unitary transformations are useful for many other purposes too. So let's change the subject slightly. Let's take the Schrödinger equation and write it in Ket language this way: as IH bar ddt applied to psi, which is understood to be a function of time, the state vector is a function of time, is equal to the Hamiltonian, which we allow to be a function of time, times psi of t. So this is in a somewhat abstract form as the Schrödinger equation, in rather general form. Now let's suppose we have a unitary operator which is is allowed to be a function of time. And let's think about defining new states. Let me call it psi prime of t is equal to u of t times psi of t. So the prime is going to indicate the state after the unitary transformation has been applied. Let's think about this. And so the problem is going to be then to find out what is the effective Schrödinger equation for the new psi, the prime psi. Well, the way to do that is to apply this u of t to both sides of the old Schrödinger equation. Let's do that. If I do it on the left-hand side, what I get is IH bar times u times ddt applied to psi vector. But that's the same thing as IH, I can write it this way, as IH bar ddt taken on the product of u of t times psi of t, and then a correction term, which is minus IH bar du dt, multiplying the old psi vector like this. And that's equal to h psi, which hasn't changed. Oh, excuse me, I multiplied through by u. So the right-hand side becomes u times h times psi of t. All right. Now then, let's take this equation and this term right here, let's insert a u dagger u between du dt and the psi. You see that puts a u psi adjacent to each other, which is our definition of psi prime. Likewise over here, let's put a u dagger u after the h, and this puts a u adjacent, again, u adjacent to psi, which is the new psi, which is the psi prime. And we've got u adjacent to psi there, which is the psi prime. So writing all this out, then I get IH bar ddt of psi prime is equal to, let me take this term over here first, and I'll come back to that one. It gives me u dagger times psi prime. That's this term. And as far as this term, I'll bring it over to the right-hand side. So we change the sign, and it becomes plus IH bar partial u with respect to t times u dagger multiplied onto psi prime. And so we can write it this way as h prime psi prime. To write it out in full, a prime version of the Schrodinger equation is h prime is this, same as we started with before, except now it's got primes, where the new Hamiltonian h prime is given by u dagger. You would have expected that. You just conjugate the old Hamiltonian. But in addition, there's another term, it's IH bar, partial of u with respect to t, times u dagger. And let me box that because that's the transformation law for the Hamiltonian under the unitary transformation. Now, these transformations have quite a lot of utility. For example, one can think about trying to find a u of t which simplifies the Hamiltonian so that h prime is easier to work with than h was. If you wanted to really think big and to really go whole hog with this idea, what you would do is you would say, let's find a u that transforms the Hamiltonian away completely so that h prime is 0. That's the simplest Hamiltonian of all, right? Then there's no Schrodinger equation, psi is constant. Well, what is the u that does that? Well, the answer is that it's actually turns out to be the dagger of the time evolution operator, what I previously called u of t comma t0. Not to be confused with this u. This u is used to make a transformation. That one was the time evolution. But if this u is the dagger of that one, then this transformation I just talked about is exactly the one that converts to the Heisenberg picture, in which the h prime turns out to be 0. So you can that's in some sense is the philosophy of the Heisenberg picture. You can imagine more modest goals, however, which instead of trying to transform away the entire Hamiltonian, you transform away a perturbation. Or maybe the Hamiltonian has rapid time dependence in it, such as you're interested in the motion of an atom in an ion trap, which is a very common problem these days. So there's high frequency terms in the Hamiltonian, and you'd like to get rid of them. That can be done by this kind of a technique. So this is a very common and important technique for a lot of applications, and we may well come back to it later in the course. So right now I have a more limited goal, a more immediate goal, which is to use it for doing a gauge transformation. So let me show you how that works. Let's go back to the Schrodinger equation. Let me write the original Hamiltonian h as pi squared over 2m like this, plus a q phi of x and t. And I can write this as kinetic plus potential, if you will, like so. And the pi is given by 1 over m times, excuse me, there's no 1 over m. Pi is given by p minus q over ca, which is a function of x and t. And of course, the potential V is given by q phi, which is a function of x and t. So as you can see, we're going to need two terms in computing h prime. We need to conjugate h, and we have the time derivative part. Well, first I need to say what u is. So here's the u that we're going to use. Let's set u, which will be a function of time, to be a phase factor, e to the I, some phase function alpha, which is a function of x and t. Now, I'm using operator notation here, so u is an operator, and so the x that's here has to be interpreted as the operator x. So if you want to really be careful about that, I could put a hat on it to emphasize that that's the operator. However, if I took psi and mapped it into psi prime, which is what I want to do, in fact, as u of t times psi, then the corresponding effect on wave functions is that psi prime of x and t is just equal to this phase factor e to the I alpha of x and t times the old wave function psi of x and t. So all we're doing is changing the phase of the wave function by a space and time dependent phase factor. Let's choose the u to be that. This is clearly a unitary operator. U dagger is just e to the minus I alpha. All right. Now then, we're going to need to, when we compute u times h times u dagger, let's first work on the UH. And the H has got kinetics plus potential. Let's first work on u times the kinetic energy. Kinetic energy is pi squared over 2m. So let's work on what u does to pi. So let's take a look at the commutator of u with pi. Let's look at that. I mean, see, u times pi is equal to pi times u plus the commutator of u with pi. So let's work out this commutator here. Well, pi has got a momentum part and it's got a part with a vector potential that depends on position, but u is a function only of position, so it commutes with any function of position, namely a. By the way, it also commutes with phi. So u commutes with that. What u does not commute with is the momentum p. So this is the same thing as u commutator with p, which is the same thing as the phase factor e to the I alpha of x and t commutator with p. And by simple commutator manipulations, this is the same thing as IH bar times the gradient of the phase factor e to the I alpha. And that's equal to minus h bar grad alpha times the phase factor e to the I alpha, like this. And so what we can say is that this commutator is minus h bar grad alpha times u. You can write it that way. All right. Now, notice what this does to u pi. This is u times p minus q over ca. And if we bring the u through to the other side, it becomes the p gets the p is this is the other side. So this is something times u. It's going to look like this. This is the other half of the commutator. The commutator itself is minus h bar grad alpha, and then we still have the minus q over ca, which the u commuted with. All right, so this is what happens when I pull the u through pi. Now, look at this thing here. I can write this way as q over c. In fact, let me do this. Let's do this. Let's make a particular choice for alpha. Let's let alpha of x and t be equal to q over.
Please, Professor?
Yes. Oh, thank you for telling me. I would never have noticed. Yeah, thank you very much. So I'm going through the algebra of commuting u through the kinetic energy operator, really starting with the canonical the kinetic momentum pi. So let's let this phase factor alpha, which up to here was arbitrary, let's write it as q over h bar c times f of x and t, where f was the gauge scalar that was used in doing a gauge transformation. The reason is if I make that choice, let me box it because that's the connection we want with the gauge transformation. The reason is if I make this choice, then this pair of terms that occurs here is the same thing with a minus sign as a plus the gradient of f, which is the same thing as minus q over c times a prime. And so we can summarize this by writing u pi is equal to pi prime u. That's to say, when you pull u through the expression for the kinetic momentum, you get the prime version for the kinetic momentum. That's to say, in the new gauge, it converts the a to the a prime. And so if I pull this through the entire kinetic energy, what I get is the prime version of the kinetic energy with u, because t is just pi squared. Just pull it through pi twice. Each pi gets converted into pi prime, where t prime is equal to pi prime squared over 2m. And if we're to be explicit, pi prime is equal to p minus q over c a prime, the gauge transform potential. All right. And so if I do all of that, then what this means is that u dagger is equal to t prime in the kinetic energy. Now, what about the q phi term? What about the potential? Let me do it this way. What about the potential energy, u dagger? This is the same thing as u times q phi, which is a function of x and t, u dagger. But that's just equal to the original potential. It doesn't change because the phase factor commutes. Being a function of x, the phase factor commutes with any other function of x, such as the potential. So go back to my transformation law for the Hamiltonian. The UHU dagger converts the vector potential into the new one, but it doesn't do anything to the scalar potential. However, this time-dependent term is going to fix that up. And if you go through the algebra of that as well, what you'll find is that if I add the IH bar, partial of u with respect to t times u dagger, you'll find that this is equal to q times minus 1 over c df dt, which is the correction term you need to convert phi into phi prime. And so the result is that the new Schrodinger equation looks like this. It's 1 over 2m. It's 1 over 2m momentum p minus q over c a prime of x and t, quantity squared, plus q times phi prime of x and t. This whole thing multiplies onto psi prime of x and t is equal to IH bar partial with respect to t of psi prime of x and t, where the psi prime and psi were related by the phase factor. I wrote it down earlier. Is it easier to find it, or is it easier just to write it again? I'll write it again, is that psi prime of x and t, it's equal to e to the I alpha times the old phase factor, but the alpha up above here, you can still see it's given in terms of f. So this is, let me write it out. This is e to the iq over h bar c times f of x and t times psi of x and t. And this is to be coupled with the transformation for the vector potential, which is the old vector potential minus the gradient of f, and the scalar potential phi, which is equal to the old scalar potential. Phi prime is the new one, the old one is phi. This should be a plus sign here, minus 1 over c df dt. So you see, when we come to the quantum mechanics of charged particles in electric and magnetic fields, especially the magnetic field is the issue here. We bring it up so we can see it better. We not only need the laws of gauge transformations of the potentials that come from just classical electromagnetic theory, but we also need to change the wave function. The wave function is gauge dependent. It depends on your convention for the vector and scalar potentials, amazingly enough. Now, this only applies for a particle with charge, Q, electron, for example, but in the case of charged particles, the wave function is gauge dependent. Now, notice that this is just a space and time dependent phase factor. So if you square it to get the probability density, it's the same both before and after. And you would expect that because the probability density is something you can measure by counting particles that end up in some region by repeating your experiment over and over again. And it shouldn't depend on your gauge convention. And indeed, it does not. However, this also is relevant for the question that sometimes arises, which is, how do we measure the wave function? How do we know, well, more generally, how do we know what the wave function is? But another way to say it is, how do you measure the wave function? And the answer is that usually you don't measure the wave function. For one thing, there is no wave function for a mixed state. So if you're going to measure it, you better make sure you got a pure state to begin with. But on top of that, what these results show is that although you can measure psi squared, you can't measure the phase of the wave function psi without having a convention for a gauge, for a choice of gauge for the electromagnetic fields. It's a very strange situation, but that's how it is in quantum mechanics. All right. So this is kind of an introduction then to charged particles and electromagnetic fields in quantum mechanics, and I think that's all I want to say about it. Are there any questions about it before we go on to the next topic?
Could you repeat what you were saying about the Heisenberg picture and how it relates to this unitary transformation that we make? Like, is there something about how?
Yeah,
I think I was just confused.
yeah. So So I made a digression into what happens when you do generally time-dependent unitary transformation on your system. You transform your state vectors by that transformation. Being unitary, it doesn't change any scalar products. So the same both before and after the unitary transformation. So measurements in particular aren't affected by it. But what it does do is it transforms the old Hamiltonian into a new one, which may be easier to work with than the old one was. Oftentimes, this is the strategy of doing that. So we worked out a formula that shows what the new Hamiltonian is in terms of the old one and the unitary transformation operator. Now, if you're trying to simplify the Hamiltonian, you've got an old one that's ugly and you don't like it, and you'd like to find a new one that's easier to solve. I mean, like I say, think big. Make your new Hamiltonian really simple. Make it, don't make it a free particle. Make the thing zero. Transform it away completely. Make the new Hamiltonian h prime equals to 0. Well, then the new Schrodinger equation is just IH bar psi equals 0. Psi is constant. There is no Schrodinger equation. There is no time-dependent Schrodinger equation anyway. Well, what you've done is you've made the transformation from the Schrodinger picture to the Heisenberg picture by doing that. And in fact, the U of t that's required to bring that about is the dagger of this time evolution operator that we talked about earlier, which connects the Schrodinger and Heisenberg pictures. Does that answer your question?
I think so. So can you think of time evolution as a special case of a unitary transformation?
Oh yes, certainly, because the time
Okay.
evolution operator is unitary. It has to be in order to preserve probabilities.
I see.
And so remember, there's a version of the Schrodinger equation which doesn't involve state vectors, but rather involves the U operator. It's essentially the same equation, but it's an operator equation instead of a cat equation. And in some
Okay,
cases, we can actually solve that equation. Okay. Now, in other circumstances, your ambitions are not so grand. You just want to simplify the Hamiltonian, not transform it away altogether. This is where things like interaction picture come in and so on. All right. In any case, what I've been through here is to show you that a gauge transformation is actually a unitary transformation. This is one of the ways of looking at it. That is to say, it's a unitary transformation on your state vectors. All right, if there's no more questions about that, I'm going to move on to the next topic, which is WKB theory. I'm going to try to be.
Hi, Professor, could I ask a question?
Yeah, sure.
I guess it occurred to me during this analysis that the charge, this Q, we've just assumed that it was like a scalar, like a classical C number. And was there any reason that we did that we assumed that it?
Well, it isn't. That's what it is in classical E and M. So we're doing E and M here. Is the electromagnetic charge is a scalar.
Yeah. Okay.
Okay. I mean, yeah.
But like position is also, I guess, well, it's a vector, but it's not an operator until we introduce
No. Position is an operator and charge is not.
Mhm.
Charge is a characteristic of the particle.
Okay.
Now, I mean, there are sophisticated theories that reinterpret charge as being an operator, but like field theories and so on, but that's not the point of view we're taking here. Charge is really a parameter of the characteristic of the particle.
Okay.
Okay.
Okay, thanks.
All right, so let's talk WKB theory, or more generally what's called semi-classical mechanics. In my opinion, one of the main reasons for studying this subject is because of the incredible and lovely and rich and beautiful structure that reveals between classical mechanics and quantum mechanics, and also because of the insight that gives you in dealing with quantum problems. It also has the advantage of giving you useful approximations in many cases in quantum problems. Usually in one-dimensional problems. WKB theory is a little disappointing in multi-dimensional problems from a practical standpoint. It sometimes works, but it's much more difficult in many dimensions. In any case, let's proceed with it, and I hope I can convey some of this. I'll just get started, and I hope I can get some progress on it. So to begin with, I'm going to begin by just working through some examples. This is going to be a challenge to my artistic skills. Let me begin by sketching a potential energy, which is a potential energy for an oscillator. It could be a harmonic oscillator. So as a function of x, we have a potential V of x. Let's see, can you all see this here? Yeah, okay. So let me see how good my artistic skills are, i.e. not very good. Let me draw the potential here. It doesn't have to be a harmonic oscillator. In fact, it could be a lopsided potential. Let me draw it deliberately, kind of lopsided, like this. And let's say we've got an energy here, like so. And so there's two turning points there and there, which if I bring them down to the x-axis, I'll put the dots here on the x-axis here for the turning points. And so as a description of the classical mechanics, the particle just oscillates between these two turning points, goes back and forth forever and ever in a cyclical fashion. There's a single cycle with a given period. The velocity goes to zero at the turning points and reaches a maximum at the bottom of the well, accelerates downward and then decelerates coming back up. So that's all simple classical mechanics. Now, let's look at the quantum wave function. Let's suppose in particular the energy E that I've chosen here is an energy eigenvalue of the quantum problem. So there's a wave function that's associated with it. I'm talking about an energy eigenfunction now. Let me draw a horizontal line here. And so this is going to be psi, and this is going to be x here like this. And let me bring the turning points down here because they're relevant too. Again, put a dot on the x-axis here and bring the dotted line down as best I can for the turning points. And do the same one for this one here, bring this down like so, and then continue on down like this. So if you take a solvable problem, or even one you do numerically, and you just plot what the wave function looks like, I'll sketch it for you for a reasonably large quantum number. In the notes, I've got sketches or computer plots of harmonic oscillator eigenfunctions that you can look at. But anyway, here's generally what it looks like. In the first place, there is an envelope function, which goes something like this. Let me draw the envelope function in red to make it different from this. It kind of comes down maybe something like that, and then it goes up like that, and then likewise down here it's going to go, it goes up like this, and then it goes over like this and comes up. There's some kind of envelope function that's symmetrical on the two sides. As far as the wave function goes, it dies off exponentially in the classically forbidden region. So over here it does that. Then it rises to a rather high maximum near the turning point, and then it goes down. And it comes down, and what it does is it kind of follows the envelope, like so.
Sorry, can you clarify one thing?
Yes.
You said that the envelope was symmetric on two sides, but the potential is not symmetric. So where's the axis of symmetry here?
Yeah, the envelope is symmetric about reflecting this way. The potential is not symmetric that way.
Okay, yeah.
Okay, that's what I meant to say. The envelope function is not symmetric that way either if the original function is not. I meant about momentum. So the lower branch is a reflection of the upper branch. All right, so the quantum wave function just kind of oscillates between this envelope red lines. And as we move in towards the origin, the wavelength gets shorter. So let me try to sketch that. My artistic skills are not good, but we get shorter wavelengths coming in like this. And then you get this kind of stuff and it comes up here like this. And then on the other side, it kind of does this in reverse. The wavelength is initially short, but then it starts to get longer. And it just oscillates between the potentials like this, between the envelope function like this, wavelength getting longer and longer. And I probably don't have quite room to do it all together, but it finally comes up to one grand maximum like this, and then comes over like this and dies off exponentially. So real wave functions look like that, you know, for 1D problems they do anyway. And look in the notes to see a harmonic oscillator example. All right. So there's a couple of features of this that you have to ask why do they have these features? Why is there this envelope like this? You see, what determines this red curve? That's one question. Here's something else that arises as well, is this wave function, of course, has a wavelength. As to say, we can take a look at, say, two successive crests like this, and we can look at the distance between them, and we can call that lambda. But the lambda depends on position. As I explained, the wavelength gets shorter down here near the bottom of the well, and it gets larger as you move away upwards towards the turning points. I tried to sketch that there. So you've got a wavelength lambda that's a function of x, basically. It depends what x value is. Now, de Broglie tells us something about about free particles, he tells us the lambda is 2 pi h bar divided by a momentum p. This applies to a free particle. But de Broglie's wavelength is just a characteristic of the the wave function of the free particle. It's not a function of x, and we've got a function of x here. Does this mean, following de Broglie, that we have an x-dependent momentum p of x like this? I wouldn't write it down if it weren't true. It does imply that. But what does this x-dependent momentum refer to? Well, back up in the classical particle, bouncing between the turning points, there is a momentum that depends on position. It's just the momentum of the particle depending on where it is. You see, the total energy of the system is p squared over 2m plus v of x. That's equal to the energy E, which is also equal to the classical Hamiltonian. I'll just put an H on that, but that's a classical Hamiltonian. So this is just kinetic plus potential is all it is. But for a given energy E, it allows you to solve for the momentum P in terms of X. And so what you get is you get P of X is equal to, if I have room to write it here, it's a square root of 2m times E minus V of X. Actually, there's two momenta because it comes in with P squared. There's a plus and a minus. I'll come back to that later. But now the question then arises, is this spatially dependent momentum that comes from the quantum wave function equal to the classical momentum at the same point? Like here's this, bringing this up here, these two peaks are close together. Is that lambda and is that lambda from this quantum wave function related to the P of the classical particle at the same place? And the answer is yes, it is. That's where it is. And that's what determines the spatial dependence of the local, what you can call the local wavelength of the quantum wave function. It gets closer together near the bottom of the well because the momentum is larger, and therefore the de Broglie wavelength is smaller. And the wavelength gets larger as you move towards the turning points because the momentum is going to zero, and so lambda, the de Broglie wavelength, gets larger. In fact, nominally, notice please that exactly at the turning point where the momentum goes to zero, the nominal de Broglie wavelength goes to infinity. Well, you can't draw a wave function with an infinite wavelength, and we don't see that here anyway, but we do see a rather wide looking lobe here at the turning points, and that's related to this nominal divergence of the de Broglie wavelength at the turning point. So the wavelength features of this wave function are explained in effect by the classical orbit. All right. There's something else that's going on here too, is there's approximations that are going on. I deliberately drew this for a reasonably large quantum number. Here's one obvious approximation that's taking place here is that the change in the wavelength lambda okay, what I mean by delta lambda is I mean the change in the wavelength lambda as I move from one wavelength to its neighbor. That is to say, delta lambda in the distance of lambda divided by lambda, that's a dimensionless number. That's much less than 1. That's to say that the wavelength is changing slowly. When I say something is changing slowly, I mean it's changing slowly on the scale of a wavelength. So the lambda is changing slowly. By the way, this red curve is an amplitude. We put it in red. We call it A. It's an amplitude, you see, of the wave function. Notice the amplitude is also changing slowly. It doesn't change much on the scale of a wavelength. Okay. Now, there's something we can do here. We can make a table here of various quantities, some that we'll call classical and others that we'll call quantum. And I'll call a quantity classical if it has a meaning in the classical problem. So that includes the energy and the momentum and the position x and some others that I'll list in a minute. And I'll call something quantum if it does not have a classical meaning. That includes things like the de Broglie wavelength. The h bar itself doesn't have a classical meaning. The wave function psi doesn't have a classical meaning. We can maybe list a few other things as well. So what's happening here is you can see that the wavelength, if the momentum, as I just explained, is classical, but the wavelength it has an h bar over p, and so that makes lambda itself a non-classical object. In fact, you can see that lambda, the wavelength, is small compared to the separation between the turning points. In a sense, it's small compared to classical scale lengths of the problem. Classical scale length is the distance between the turning points. That corresponds to the notion that h bar is small. As a practical matter, h bar is small in typical classical problems, like solar systems and so on. But h bar is not dimensionless, so to say that it's small, you really have to state it in dimensionless terms. That's part of what I've done here. Delta lambda over lambda is dimensionless, and this is a meaningful statement here regarding orders of magnitude. But in spite of the fact that h bar has dimensions it's not dimensionless. The classical limit of quantum mechanics is, in a certain sense, one in which h bar goes to 0. Let me explain a little bit better what that means. The way to think about this is to imagine holding all the quantities that have a classical meaning fixed, E, P, X, and so on. So, for example, that would mean we'd hold this picture up here fixed, this classical picture, the turning points would be fixed, they wouldn't change, and so on. But what we then do is we let h bar go to 0. So you can see that if you let h bar go to 0, the de Broglie wavelength, or let's say you cut h bar in half, suppose you did that, then the de Broglie wavelength would get cut in half too. And the way this picture would change is that you get twice as many oscillations in here with a wavelength that's only half as big. But the envelope would still look the same, and otherwise the picture would pretty much look the same. So this is part of what's involved in going to the classical limit is that as h bar goes to 0, you get finer and finer oscillations. The wave function itself doesn't approach a limit at all. It just oscillates ever more rapidly. It's what you call an essential singularity as h bar goes to 0. The wavelength lambda goes to 0 and loses meaning. But these things stay the same. They're independent of h bar. And so this is one way of understanding the classical limit. So in particular, the local de Broglie wavelength has a classical meaning, and it's related to the classical mechanics of the particle it's moving. The amplitude, it turns out, also has a classical meaning, which I'll explain in a minute, but I'm not ready to do so now. Anyway, this is an overview of how classical mechanics gets connected with quantum mechanics in a one-dimensional WKB problem. Not solving any equations, but just giving you hopefully an intuitive idea of some of the issues that are involved. All right. Now then, I'm not done with this 1D example yet. I want to make a few further points. One of them is that, let me bring the piece of paper up. One of them is, if you just look at this wave function, it's obvious that there's an approximation, at least that the psi of x is, let me make it approximate here, is the amplitude A of x, that's the red curve, times a cosine of a phase phi of x. Okay, and in other words, it's a cosine that's modulated. That's the amplitude modulates it, cosine wave. And what the phi of x is going to take care of is the fact that the wavelength is a function of position. Now the phi of x is the accumulated phase relative to some initial point. Let's say if I started here as my initial point x0 and over here was my final x, like that, then the accumulated phase is 1, 2, 3, 4, 5 times 2 pi. That's what phi would be. Now, on the other hand, if I cut lambda, if I cut h bar in half, then the number of wavelengths would double, and so phi would double as well, because there's now twice as many oscillations in the given interval. So what this shows you is that phi of x as a numerical quantity, how it scales with h bar is it goes like 1 over h bar. So let's take phi of x and let's write it this way. This is a definition as s of x over h bar, where s of x is now independent of h bar. So just by that simple substitution, I've got a of x times cosine of s of x over h bar. Now, the reason for doing that is the s of x now being independent of h bar, you see, becomes a classical quantity. I can put it over here on my classical side like this. We'll see what it is later on. It's actually the classical action. But anyway, that's what we did by looking at how things scale or how they depend on h bar in this scaling system. This cosine, of course, is a linear combination of two waves, complex waves. They would look like this: is a of x times e to the plus and minus I over h bar s of x, like so. Linear combination of these things, complex waves. And as we'll see when we get further along, these two waves with the plus and minus sign represent WKB waves, one of which is traveling in this direction and the other is traveling in that direction, corresponding to classical particles that are moving this way and those that are going back on the other return half. and the oscillations here that you see, the cosine oscillations, are the interference between the two waves going in the two directions. All right. So in some sense, these complex waves are independent solutions in this inner region, and it's a linear combination of the two is needed for boundary conditions, but it's a linear combination of two that gives you the oscillations that I've sketched here. All right. Now then. Okay, so let me think a little bit about what I want to say next here. I think the next thing to say is let's use this one-dimensional. This is all intuitive, of course. Let's use this one-dimensional picture and intuition we've developed in order to do something in 3D now. Lock this again. Let's move to 3D. In 3D, this wave function, let me call it psi of x here, going back to the 1D. Psi of x is equal to this. I'll call this the WKB ansatz. It's sometimes described by saying that you have a wave with a slowly varying amplitude and a rapidly varying phase. It's rapidly varying if h bar is small, you see, because then a small change in S of x produces a moderate or large change in the phase. Let's generalize the WKB ansatz into 3 dimensions. It would be psi of x is equal to an amplitude a of x times e to the I over h bar times s, which is now a function of 3-dimensional x. Let's suppose we find a solution of the Schrodinger equation, which is equal to this, at least approximately. And indeed, it turns out you can do so. Let's suppose we do this. Then what does that wave function look like, and how is it related to classical mechanics? That's the next question I want to address. Well, S of x, apart from the factor of h bar, S of x is the phase of the wave function. So this wave function has phase fronts. Let's sketch one of the phase fronts. It's a contour surface of S, is where S is constant. S is just any old function. We don't know what it is because we haven't solved the problem, but it's going to be some curved surface. Presumably it's a curved surface, right? It's a reasonably complicated problem. So let's sketch a part of the surface, might look like that. So let's say S of S is equal to S0 is one contour surface. Let me sketch another contour surface like this, which lies behind it, like so. And let's say this is S of x is equal to S of 0 minus 2 pi h bar. Let's make it that one there. Now the reason I did that is because adding or subtracting a multiple of 2 pi h bar to the function s, since we're dividing here, is just adding or subtracting a multiple of 2 pi to the phase. So these two surfaces I've sketched here are two successive phase fronts, you see, of this wave function. And you can imagine then these phase surfaces stacking up. They're generally they're curved surfaces stacking up and filling up space, and thereby giving you a picture of what this wave function looks like. At least insofar as the phase is concerned. It's oscillating, you see, in this direction. Now then, let me take a point in this surface S, and let me draw the gradient of S, which is of course orthogonal to the surface. The distance between the two surfaces here is lambda, it's the wavelength. So let's look at what that implies. Remember, in the 1D problem, we had the momentum p was equal to ds dx. That's what came out of the 1D problem. Did I do that in the 1D problem? I don't think I did that.
No.
No, I didn't. Let me go back and do it, because let's do it in 1D first. Let me do it this way. Let's go back up here to where we had the 1D results. The wave function is a of x e to the I s of x, I over h bar s of x. So the phase is s over h bar. So that means if I increase the phase by lambda, that's got to be equal to s of x over h bar plus 2 pi, because that's the definition of lambda. But let's write this as s of x over h bar plus lambda times ds dx over h bar. Just expanding s out to first order in lambda like so. And if you do, you see the leading terms cancel, and we can solve for lambda here, and what we get is lambda is equal to 2 pi h bar divided by ds dx. And so what you see is that in the de Broglie interpretation, you see the momentum p is equal to ds dx. So going back to this picture then, this very nice picture we had here about the local de Broglie wavelength here being related to the momentum of the classical motion, that also gives us a relation between the momentum p and the phase s of x, or the phase is s over h bar, namely that p is a derivative of s. You see, it makes sense because s is the total, s over h bar is the total phase. So as you move along here, s is just accumulating and growing as you move along. You just measure the distance that's involved in making s over h bar change by 2 pi. That's what you mean by lambda. So it's clear that lambda is related to the derivative, and lambda goes like 1 over p. So that provides a connection between the momentum and the derivative of the phase s, the phase function s. Now, if we do this in 3 dimensions, the gradient of s is now a vector, which is orthogonal to the phase fronts. How is this related to the momentum? Well, it turns out it's equal to the local momentum p, like this, a momentum function. There's various ways of seeing this. One fairly simple way is just to look at this in a reasonably small region where the curvature of the phase fronts is not significant. If you do that, then you've got essentially plane phase fronts, like so. So that locally it looks like a plane wave. E to the I p naught dot x is what the plane wave would look like over h bar. And so the action function you see is basically p naught dot x. So the gradient of p naught dot x is of course equal to p naught. The gradient of the phase function is in effect is the local momentum. And so this generalizes into curved surfaces and gives us, it generalizes the 1D result and gives us a momentum then, which is a gradient of s. But the s is a field because as I mentioned, I'm saying, let's suppose we solve the Schrodinger equation and we find a solution which is at least approximately in this form. That means s is a function of position, so its gradient is also, it's just like the lambda dependent, the lambda dependent de Broglie wavelength in the 1D problem. Here what we've got is an x dependent momentum. So what you get now is a momentum field, which is to say, i.e. p is a function of x, and it's equal to the gradient of s, like this, which is associated with the solution of the Schrodinger equation. Now, based on the 1D picture, what that suggests is that this solution of the Schrodinger equation is associated with in effect, not just a momentum field, but a collection. It's as if there are different momentum at each point. It's as if there's a different classical particle at each point. Imagine space filled up with classical particles such that the particle at position x has the momentum p of x. This then is a way of associating the solution of the WKB, or the WKB form solution of the Schrodinger equation, with an ensemble of classical particles which define a momentum field. To go back to the 1D case, we can talk about that just as well. We originally spoke of a single particle oscillating between the turning points, going back and forth like this. There's a different point of view, however, which is to say that instead of having a single particle that's oscillating between these turning points, let's have an ensemble of particles that are in effect moving each other around and around, chasing each other around. They all follow the same orbit, but with different time delays. So in effect, there's an ensemble of particles oscillating back and forth like this. Then the particle, which is at position x, has a momentum given by this formula, which is related to the de Broglie wavelength of the corresponding wave function. Now, if we carry that over into 3D, it means that in some region of space in which the wave function looks like that, at a position x here, where we've got phase fronts that look like that, and a gradient which is orthogonal to the phase fronts, we associate that with a momentum and thereby say that at that point, there's a classical particle that has that momentum p. This gives us an ensemble of classical particles filling up configuration space which provides a classical interpretation for the quantum wave, which is emerging from the solution of the Schrodinger equation. Okay, so this is part of the three-dimensional generalization of that picture that I gave you in 1D. Yes, question.
So that one point is only for one of the contours of S. If we were to trace that point backward, would that give us the trajectory of that one classical particle?
Yeah, so you're asking really good questions. So let me try to outline the logic carefully. If we assume that we can solve the Schrodinger equation, at least locally, and come up with a solution that at least is approximately looks like that, which in fact you can do, then this function S of x, which except for the h bar is the phase of the wave function, it not only defines phase fronts, which are these surfaces, stacked surfaces like this, but it also defines a momentum field, P of x, like this. Now that momentum field we can interpret as being the momentum field P evaluated at a position x, we can interpret it as being the momentum of a classical particle located at x. So let's suppose we go around and we fill up configuration space or some region of it with such particles with momenta, which are determined by our quantum wave function. Those particles, of course, have an energy and they also have a velocity, don't they? Because they're functions of momentum. The velocity is just P over m, and the energy is given by the classical Hamiltonian, P squared over 2m plus potential energy at the point x. Okay, so they have an energy and they have a momentum. Well, what do you think the energy is? I'm assuming this is an energy eigenfunction of the quantum of the Schrodinger equation with some energy E. That energy of those particles turns out to be that energy E, the quantum eigenvalue. Also, they have a velocity too. What about the momentum? That momentum P. Does that momentum P, if I square it to get a kinetic energy and add it to the potential energy, does that give me the energy E? Yes, it does. But now you're asking a different question. You're saying, suppose I now follow these particles in time. I mean, I'm giving initial positions and momenta for each of the particles. So that's complete set of initial conditions for the classical motion. So let's turn on the classical motion, let the particles move. They move to a new place. What do? When they get to the new place, do they have the momentum that's predicted by the wave function or not? The answer is yes, they do. Turns out they do. So in other words, in effect, the waves are carried forward by the motions of the particles. You see the particle is moving, of course, in the direction P, that they're actually moving perpendicular to the phase fronts here. They, in effect, carry the phase fronts forward with them. All right, so.
So does this mean that this is actually the kinetic momentum and not canonical momentum?
Well, I'm doing a kinetic plus potential problem here. So yes, there's no difference. If you did it with I don't want to confuse things by bringing in magnetic fields. Let's talk about that in office hours if you want to do that. But it's an interesting generalization though. In that case, the particles don't move orthogonal to the phase fronts. They follow the canonical momentum, not, excuse me, they follow the kinetic, the canonical momentum is let me skip it because I'm afraid I'll just confuse things if I go into it right now. Ask me in office hours and I'll be glad to tell you about it. Okay. But for a kinetic plus potential problem, the particle orbits are orthogonal to the phase fronts, and you can visualize them as carrying the phase fronts forward with them as they move along. All right.
So this momentum is always the kinetic momentum rather than the canonical.
I'm only doing a kinetic plus potential problem, so that's all it is here. If you want to draw the distinction, as I say, let's talk about it in office hours. I'll be glad to do that.
Okay.
Remember, when you change the gauge, you change the phases, so it's going to change the phase fronts. So those are issues that arise there.
Got it. Thank you.
Okay. Well, I used a lot of time giving you all of this intuitive picture, and I hope it was worth it. Let me now get into some real calculations. Let's take the ansatz psi of x is equal to an amplitude a of x times a phase, which I'll write as e to the I s of x over h bar, following the hints that we've seen starting with a 1D problem. We don't expect this to be an exact answer, but an approximation. So I'll write it as an approximate answer like that. But the idea should be that I should be able to plug this into the Schrodinger equation and find equations for A and S. That's the strategy, that's the plan right now. But to do this, we need to be a little bit careful about it. The Schrodinger equation in question depends on what Schrodinger equation do I want, by the way. Let's do a, so one comment here is that WKB theory can be used for any kind of wave equation. It can be used for 1D, 3D, time dependent, time independent. It doesn't have to be a Schrodinger equation. You can use it for light waves, sound waves, gravitational waves. It's a general method for dealing with wave systems, especially linear wave systems, when the wavelength is short. That's sometimes called a short wavelength approximation. But anyway, in quantum mechanics, let's write down a specific wave equation that we want to talk about. So let's do the Schrodinger equation, time-independent Schrodinger equation in a potential, kinetic plus potential problem equals E psi. Let's take this as a sample problem, an example, non-trivial, but common problem that we were interested in solving. Let's say we want to solve that. And then the idea is to try to plug this ansatz into this equation and get equations for A and S. So I think I'm going to outline how this works. So in the first place, let me write this ansatz this way: is e to the I over h bar times s of x minus I h bar times the logarithm of A. All I've done is I've taken the amplitude and bring it up into the exponent and looked and ordered it like that. The reason for doing that is that it shows that the exponent written this way is I over h bar split off, and what's left over has an order 0 part and another part which is order h bar. It sort of looks like the beginning of a power series in h bar. The thing in the square brackets is the logarithm of the, apart from the I over h bar, it's essentially the logarithm of the wave function psi, as you can see. So what's beginning here is a power series expansion of the logarithm of the wave function. By the way, if you're going to do the most naive thing, didn't know anything at all, and somebody said, get the classical mechanics out of quantum mechanics, you'd say, because that's when h bar is small, you'd say, oh, let's expand the wave function in powers of h bar, right? But that doesn't work because the wave function doesn't have a limit as h bar goes to 0. Instead, it just oscillates ever more rapidly. On the other hand, the logarithm of the wave function can be expanded, and that's what we're doing here. So the most efficient way to do this is to write it this way: is e to the I over h bar times function w, which is 3D here. Let me write this as psi of x like so, is equal to this. And then we'll write w of x as a power series in h bar, which in principle includes all powers. And you can carry it out to any order you want like this. So let's now, in effect, not make any approximation here. This is the exact psi, but we're going to let the exponent go out to arbitrary order in h bar. Now, it's then straightforward algebra to take this psi and to plug it into the Schrodinger equation. I'll sketch the algebra for you. The gradient of psi is equal to I over h bar gradient w times psi. Laplacian psi del squared psi is equal to I over h bar del squared w minus vector grad w squared over h bar squared. That whole thing multiplied onto psi, taking the two derivatives. If I then take this del squared psi and plug it into the Schrodinger equation up above, the other terms are v psi and e psi. Now the del squared psi is proportional to psi. And so I can cancel the psi here and there and there. And I get an equation just in W. This needs to be multiplied by minus h bar squared over 2m. So here's what we get. We get 1 over 2m del W quantity squared. That's that term. This term becomes minus I h bar over 2m times del squared W plus the potential V of x is equal to the energy E. Now, this is an exact result. We didn't make any approximations. It's just transforming the Schrodinger equation from psi to the log of psi. This is a nonlinear transformation. So now the nice linear Schrodinger equation has become nonlinear because the del W is squared. The next thing, however, is we want to solve this equation approximately order by order. And we're going to do that by plugging in this expansion here into this equation, and then get it by order h bar 0, h bar 1, and so on. And we'll see a hierarchy of equations emerge. The first of which will give us the action function S, and the second will give us the amplitude A, and then you can go to higher orders if you're motivated. Now, I'm out of time, so I'm not going to do that tonight, but that's where we're going in the next lecture then. Okay. Are there, so that's all for tonight. Are there any questions?
Yeah, so we've chosen the positive exponent here. Is that just convention?
Well, in the 1D problem, we had the two waves, I said, going to the right and to the left. So the idea is we're going to find a solution. We're going to find the solutions we can find in some region, and then we'll form linear combinations afterwards. So the simplest form for the solution is the complex ansatz like this. It's easier to work with than cosines.
Okay.
Any other questions?
Yeah, Professor, maybe I missed something. This first line, why is this an approximation? I mean, it's a complex number at space. We can always write it as like an amplitude times.
Yeah, that's a good question. That would certainly be true if you regarded this as the the decomposition into amplitude and phase, and it sure looks like that when I write it out that way. But if I did it that way, I would find that S and A have an H bar dependence, not at lowest order, but they'd have higher order terms which are H bar dependent. So if I wanted to compensate for that, I could then expand S as S0 plus H bar S1 plus H bar squared S2 and so on, and do the same thing for A. You follow me? And if I do that, then combine all that together, it's equivalent to what I'm doing here with W, which is just simpler.
Okay, yeah.
Okay, so yeah, that's a good point. Yeah. Any other? I'm getting a lot of good questions tonight. Any other questions?
What does it mean when you say things are H bar dependent, and when you take limits of H bar, when we like traditionally think of H bar as like a constant with like some numerical value, right?
Yes, yes, that's quite so. We frequently do this, if you have, in perturbation theory, you have a parameter lambda, which could be the fine structure constant or something. And you say, oh, we'll let it vary between 0 and 1, or scale it by lambda and let lambda go from 0 to 1 in order to do a Taylor series. So you do this in order to develop power series. If you don't do this, you can't argue that the separate terms are linearly independent of each other. So it's a strategy of dealing with perturbation theory. So in effect, in other words, in order to do a perturbation theory in powers of H bar, you have to at least mathematically consider H bar a variable.
So it's just something small. Is that the statement?
Well, H bar is neither large nor small if you say it correctly, because it has dimensions. It's not dimensionless. But I can take the physical value of H bar and multiply it by a parameter lambda that I allow to scale between 0 and 1. And then I can do a power series expansion in lambda. Well, formally, that's just the same thing as expanding an H bar. But the point is, it's making the value of H bar, in effect, now a variable, you see.
Yeah, okay. Got it. Understood.
Okay, so we do this for two reasons, because when we make the H bar variable go to 0, if you do it in the right way, you end up with a solvable system. And guess what that system is? It's classical mechanics. So when you do perturbation theory, you want to perturb around a solvable system. So that's what we've got. But the second reason for doing it is that it's a very interesting solvable system, because it's one we use a lot and have a lot of intuition about. Any other questions? These are really terrific questions I'm getting. All right, if there's no more questions, I'm going to, I can stop screen sharing. I'm going to stop screen sharing, and I'm going to stop the recording. One last chance for questions. All right, and here we go.